Okay, so we've now derived the weak form of the solid mechanics boundary value problem, but let's solidify it. Let's make sure we solve sort of a problem. So I've uploaded some class notes of a problem that I've solved. So what I want to do now is just quickly talk about the problem so that we can start maybe just tackling and discussing it. So let's imagine we have a problem as follows. Just at least solve our first problem, but we can now sort of enter into chapter 3 of the prescribed textbook. Okay, the problem that I have is a sort of a bar that is sort of has an area that varies. So you can think of this now as a three-dimensional square bar, and there's a linear variation of that area that we have there. So I can say area, what was the variation? A of x is equal to 0.002302 minus 0.x meter squared. This bar has got a length of, so x equals to 0 up and until x equals to 1 meter. Yeah. What else is given to the bar? Oh, it's made out of steel, 210 gigapascal. That's what we have there. What else? Then there's a load that's applied at the tip here of 1,000 newtons. Okay. So F is equal to 1,000 newtons. This is the problem that we have. So what we're going to do is say, let's solve now the weak form of the solid mechanics boundary value problem. But let's first just reason about what are the steps that are required. Make sure everything's on the board here. Yeah, so I've got this x here, so that's fine. So what are the steps that would be involved? If you just reason about what we had. Well, first off, I'm just going to conceptually talk about this. We're going to have to first, step one maybe is to say, assume a form for the displacement field. Okay, so that's step number one. If I assume a form for displacement, and I'm going to say fields here, so I've got a field that I need to assume for, call it for u, v, and w. And I'm going to do it in order 3D, so that we look at the weighted residual example that we derived for 3 dimensions, how it would work. And then it's easy to extend later on then all of these ideas to 3 dimensions. Okay, so this is the first step. And this w now is not the weighting function, it's the w that's used for the displacement in the z direction. So it's not great, but I'll try to make a w for the weighting function something else. What happens then, step 2, is what follows. Once I've assumed this, I know that the w, there's going to be a wu, x, y, z, okay? And maybe what I'll do is put explicitly in here that there's some coefficient c, some vector of coefficient c, and some vector of coefficient c. Okay, some of the c's will feature in u, some of the c's might feature in v, some of the c's will feature in w. And then the same here, but instead of calling it now, I'm going to call it w vector, the coefficient that dictate this. So it's vw, vv, x, y, z, w vector, and then v w, x, y, z. Okay, so hopefully you can distinguish between this v and the sort of jiggity, the more angular one. Okay, that's that next step. Once I have this, I can then go to say, well, if we have the displacements, so I'm going to write it down as a displacement vector. So combining this now into a vector, that is going to be some function of x, y, z spatially, and then some c coefficient. From this, I can compute strains, yeah, strain matrix. From the strains, I can relate this, compute the stress matrix, yeah. That's essentially, they're also going to be still a function. Let me just make explicit a function of x, y, z, and c. Let's rather not be too sloppy. X, y, and z, c. I can from this get my stress matrix. Yeah, this requires the material, something about the d. X, y, z, some c. And if once I've got this, I can now start, just double check here. Everything is still, okay, everything's still written here. Okay, so that's what I have there. So maybe this is why shape is not a good idea. I can see it's quite difficult to see actually. Apologies for that. Okay, so that's what I have. And then number 5, essentially, I can then say maybe we could start substituting substituting it into the weak form. Yeah, and see what we have. Okay, this is going to require us to convert this into attraction, and then once we have this, step number 6 is we could start taking derivatives with respect to big W. Yeah, and if I take the derivatives with respect to big W, I might end up with a system of equations to solve for the coefficient C. Okay, so that's essentially, just in quick terms, what is going to be required for us to go through to solve this problem. Thank you.